So, hello everybody, officially hello and welcome to the session. So, I obviously wasn't there Monday, and what one of the students told me is that we didn't get up to the drawing the product thing. So I'm going to assume we did all of these questions. Is there anything up until this point right here that you guys want to ask me questions about before we move on? Anything at all? Okay. If not, cool. And we can go back to it if you want to ask me about it later. So we're going to draw some products now. And I'm going to go in not the right order for this, but why would I do things the easy way? So I'm going to really quickly go down to the second page. And we're going to do this one right here. Just because that's the most straightforward one. So Katrina might have done this example with you guys, but I'm just going to do it as if we haven't yet. So the way we're doing Diels-Alder reactions is we're going to start out with the diene. And just like they taught you in elementary school, and maybe they didn't teach you this in elementary school, but whatever, when you're doing less than and greater than signs, they tell you to think about it like an alligator mouth, and it's like going to eat the Dienophile. So that's how we're going to think of it. So we want the mouth to be open to be able to eat up the Dienophile. So if we have it in that orientation, we're going to start at the top and go 1, 2, 3, 4. And for the Dienophile, we're just going to say A and B. And it doesn't matter really what orientation that one's in, just whatever they give it to you. Whatever they give it to you as, excuse me. So you know that carbon 1 is going to connect to carbon A. Carbon 4 is going to connect to carbon B. And we're going to start out with the diene because that's the nucleophile, and it's going to give its electrons to make a bond here. Once we form that new bond, this double bond has to lose those electrons because there's too many bonds. And that's what's going to cause this bond right here to be formed. And then last but not least, this double bond, there's too many bonds to that carbon, so it's going to move over here. Also, I'm so sorry if everyone's listening to my bird scream in the background. She's having a day. So ignore that. All right. And so in Diels-Alder reactions, we're pretty much always making a cyclohexane. So I'm always going to start with the cyclohexane base. And we just formed this bond, so I'm going to draw it in purple. We just formed this bond, so I'm going to draw it in purple. And we made a double bond right here. And that's our product. And just so we can keep track, this was the 1, 2, 3, 4 of the diene. This was A and B of the Dienophile. Any questions on the general reaction? This one is super simple. There's nothing really else to add to it. But all the ones that are more complicated are pretty much this with some spice at the end.
Oh, my bad.
What?
You're like in the way. I'm like trying to like get you out of the way.
I'm in the way? What?
Oh, wait. Oh, wait. Okay. Yeah, we were hiding your face.
Oh, okay. I get it. You guys are calling me ugly. That's fine. No,
No,
I'm
it
just
wasn't
kidding.
bad. You were just.
I'm just kidding. I literally woke up like 10 minutes before work, so I'm just chilling today. But
So there's only one double bond.
exactly. So there's only going to be one double bond left because essentially all the double bonds we started with lose a bond. I just got 2 text messages at the same time. That was weird. Okay. So now we're going to move on to a slightly more difficult one, and we're going to go back to page 1.
Let me
Nope.
ask a question.
Yes.
So,
What's up?
like, is it only one double bond? Like, always? Like, is that arbitrary, or is it
It's
always?
not always, because sometimes we have triple bonds, and that's what I was going to show you right now. We're always going to have this double bond, though. So you're always going to have a double bond between carbons 2 and 3. That'll always be there. And then we might have another one somewhere, but I'll show you when that happens, I guess. So we're going to go to this one right here. Is the alligator mouth open to this? Oh no, the awkward WebEx silence. I hate it. Okay, so no, it's not exactly open. Oh, some people joined. How cute. Okay, so no, it's not exactly open to it. It's kind of, sort of is, but I like to just turn it slightly so that it's more obvious. Ta-da. So now the alligator's mouth is very clearly open to it. And we have our triple bond. So the triple bond is going to work exactly the same way. A and B. And our diene, 1, 2, 3, 4. And now from here, we know that 1 and 4 always are connecting to the dienophile. So 1 connects to A, 4 connects to B. We move our electrons in a complicated looking circle. And again, I'm just going to start out with my cyclohexane. And wow, remove. Okay. This was a new bond. This was a new bond. And we have our double bond here. And I'm also going to number this 1, 2, 3, 4. A and B. So carbon A and B, that bond is actually also going to be a double bond, because here we had a triple bond. We only got rid of this bond. So this one should still be there. So I'm going to draw double bond. And also, we have a methyl substituent on each of those. So I'm going to draw methyl, methyl. Now we have to add this part in. And I know it was between carbons 3 and 4. So I'm just going to go ahead and draw that ring. It's kind of ugly, but you get the idea. Ta-da! How do we feel about this one? Pretty good. Okay, cool. That's good. Anyone in person?
Oh, there's confusion. It's crowd.
Okay.
So
What?
I don't know. Okay.
For 3 and 4, why'd you put a cyclohexane in there? And also, where'd you get the methyls from for A and B?
Perfect. So, for A and B, we have, hold on, I'm going to blow the system. Okay, sorry. So, A and B each have a methyl on them right here. And so that's what these methyls come from. And then this cyclohexane that we had right here, that's going to carry out into our product. So that's where I got this from. So we can pretty much count those as substituents. And that's just going to be added to the cyclohexane that we formed. Is that a little bit better?
Yeah, thank you.
Okay, you're very welcome. Any other questions in person? If not, we can just go on to the next one. All right, so we're going to amp it up just a tad in the ugliness scale. So we're going to do this one. And cool, so the alligator's mouth is open. That's chill. This thing is a little bit far away, but I'm going to leave it for now. So I'm going to say 1, 2, 3, 4. I'm going to say A and B. And for the purposes of this question, there's a lot of stuff going on, so it's going to be easier for you to visualize the final product if you leave this slanted just a tad. You could move it, but I wouldn't, just because it would be hard for me to visualize. What I am going to do, though, is connect 1 to A, 4 to B. We move those electrons in a circle again. And just like last time, I am going to start out with my cyclohexane base, because I know that's what I'm making. And I'm going to label carbon 1, 2, 3, 4, A, B. And I know I made a new double bond right here. And I know that these are the new bonds that I just formed. So now when it comes to adding this guy, like how do we do that? Well, I know that it's going to connect between carbon 4 and carbon B. And I'm actually just going to draw it exactly like it's drawn there. So bam, bam. And then I know that there is a benzene right here. I don't know why it came out like looking so lopsided, but this is fine.
Oh,
Yeah.
people said there's confusion.
Okay. What's up?
I don't know.
Do you want me to just kind of go over one more time, like how I added the substituents there?
Wait, I think someone has a. Yeah, I think someone's asking, can a Dienophile be on the same molecule as the diene?
Yes, it can. So it doesn't happen too often in this class, but there can be a couple examples where the diene and the dienophile are like attached. So in this example, the diene is this one because it's a conjugated diene. We're going to ignore this ring because it's a benzene ring. Benzene wants to be left alone. And then this double bond right here, we could use that as a dienophile.
And I think people want you to just go over it one more time, like, I guess slow, like.
Yes,
Like,
okay.
yeah.
Let's do that. So I'm going to erase this. Oh my goodness, could you chill, please? Thank you. All right. So, all right. The dienophile is this guy on the side, and he's super easy. We just do A and B, right? For the diene, we're going to start at the top, and we're going to number kind of clockwise. So it would be 1, 2, 3, 4. And this is carbon number 4. And I know that carbon number 1 is essentially going to make a bond here to A. And carbon number 4 is going to make a bond here to B. So when I draw out the product, I'm going to just start out with the cyclohexane that I know I just formed. Because in Diels-Alder, we're always forming a cyclohexane. And this is between carbons 1, 2, 3, 4, and A and B. So I essentially just filled in these dotted lines and I just turned it ever so slightly. So this line is this. This line is this. Okay, once I've reached that point, I also know I'm going to move my electrons around in a circle like this. So we have a double bond between carbon number 2 and carbon number 3. And now we have to go about filling in the substituents. So this is like one big substituent. It's like one big group. And the way that I see it is it's attached directly to carbon 4 and carbon B, right? And here we made a 5-membered ring. As you can kind of see here, if you fill in that line, it's a 5-membered ring. And then attached to that 5-membered ring, we have a benzene ring. So we're going to go bam, bam, bam. So that's where I got each of the pieces from. Does it make a little bit more sense now that I slowed it down a little bit? Okay, so someone said in the chat, basically if we draw dotted lines, then that would form the cyclohexane, and then we would draw the other parts attached to carbon 4 and carbon B, and then you make sure to edit the double bonds in the cyclohexane. Yeah, exactly. So I always just go in and fill in these dotted lines first to make the cyclohexane, like Leah said. And then I go ahead and add the substituents wherever they might be. In this case, it was one big substituent between carbons 4 and B. So I draw that. And then, like Leah said, I just go back and I double check that I did this double bond correctly. Yay, nay, in the middle.
People are...
All I heard is
I think people got it. Okay.
Got it? Okay, cool. Cool. All right, so the next one we're going to do is we're going to go up to the first page, and we're going to do Mr. Triangle over here. Or when I say first page, I really mean page number 8, but... So this guy, the mouth is not open to the Dienophile. The mouth is open facing up. And now it's weird because we have this point right here, right? But for now, we're just going to ignore that point, right? Because we can still see that this is the alligator's mouth. And we're going to redraw him so that the mouth is open towards the Dienophile. And I'm just going to draw this out because I want you guys to be familiar with the functional groups. So COH is an aldehyde. All right, so let's start numbering. For the diene, I'm going to start up here again. 1, 2, 3, 4. Ignore the point. Use irrelevant for now. And then we have A and we have B. So we're going to make our dotted line or dashed line or whatever it turns out being between 1 and A and 4 and B. Move that slightly. So again, I'm going to draw the cyclohexane as a base. And I'm going to fill in carbon 1, 2, 3, 4, A, B. I just formed these 2 bonds. Those were the dotted lines. And I add another bond here. That's what I just formed. And now I have to fill in the substituents, right? And we actually have 2 substituents here on the Dienophile. So we're going to talk about that in a second. But what do we do with this point, right? So I said to ignore it. And once you've drawn like your base, we're essentially going to connect 1 and 4 like that. So we get a bicyclic compound. And this is what it's going to look like flat. You also have to know how it looks 3D, which is unfortunate, but it's not too awful. So we're going to say, bam, nope, that's ugly. I'm so sorry. Let's redo that. Bam. There we go. So this is what...
Where the bridge came from.
Okay, great question. So the bridge is... That bridge is this carbon right there. So when we did that reaction, we flipped this carbon upward. So we turned it into a bridgehead. And then we know that, or I believe Katrina covered last time, that if we have substituents on our double bond, the dienophile always has to keep the configuration. So if it started out as a cis double bond, we get a cis product. If it starts out as a trans double bond, we get a trans product. So here it is cis, and we have to figure out whether they're both pointing up or they're both pointing down. So we're going to zoom in a tad over here and imagine this in 3D. So if it's pointing up, it'll look like this. If it's pointing down, and I'm actually going to make this a little bit bigger because it's hard to draw on. Okay. If it's pointing down, it's going to look like that. And so why is this important? Because we have a double bond right there. So through something called hyperconjugation, which you supposedly learned in Orga 1, but I know almost nobody remembers it, we can say that these two oxygens are able to interact with this double bond. So through hyperconjugation, we're able to stabilize this ring because this oxygen and this oxygen interact with this double bond. So we can call this the endo product because its substituents are pointing into the ring, versus this guy is the exo product because the substituents are pointing out away from the ring. And kind of what I was alluding to was that this is the more stable option because of hyperconjugation. And one thing I will also add here, endo is dashed, exo is wedged. Any questions just on like endo and exo, what that means, anything like that?
Okay, so sorry, just to make sure, exo is going up and endo is going down,
Yes,
like
exactly.
general rule.
Exactly, yeah. So
Okay.
exo is up, endo is down.
Somebody has
Okay, and if we were going to draw this in 2D, like in the one with purple highlight, that one would we just we would just draw it like wedge and dash, right?
Exactly.
Or no?
Yeah, so that's what
Okay.
I was just going to fill in. So that's why I put the little parentheses, because this just translates to wedged. This one translates to dashed. And I heard that someone had a question in person.
Alright. So what's the product that we made, and what's the
Let
question?
me show you. So the product is this, which in 3D looks like this.
So somebody asked, how do we know it's endo?
So in this class, endo is always going to be favored because it's more stable. Since this is pointing down towards the double bond, we can say that they are stabilizing one another. So this whole system is more stable. So that's what's favorable.
And that's just across the board?
In general, no. In this class, yes. So in this class, you could treat it like a rule, like endo is always favorable. But in general, like if you go on to other chemistry classes, that doesn't apply to everything.
But both products would form. Like a little bit of exo would form, or just
So in reality,
endo?
yes, a little bit would form, but like for the purposes of his questions on the exam, if he asks you what the product is, you're picking this. Even if this one was an answer
Okay.
choice, you have to pick this one.
Okay. Thank you.
You're very welcome. All right. So I'm going to zoom out. And I want to do this one next. So the good thing about this one is it's already oriented properly. Yay. And now this one has this double bridge situation. So we just got to keep that in mind, right? We're going to ignore it for now, but once we draw the product, we have to keep that in mind. So I'm going to say 1, 2, 3, 4, A, B. And I know that 1 and A connect, 4 and B connect. And I'm going to zoom out and scroll just a tad. So, as always, I'm going to draw my cyclohexane base first. I'm going to make it kind of big so it's easy to see. My goodness, could you chill? There we go. So I'll number it 1, 2, 3, 4 again, A, B again, just so we can keep track. And we made a double bond here between 2 and 3. And we know these are the double bonds, these are the single bonds that we just formed. Now let's take care of the bridge first. Bam, bam, bam. So now instead of like 1 point in the bridgehead, we're going to have 2 points in the bridgehead. And I'll show you what that looks like in 3D in just a second. But this double bond started out as trans. So we're going to have them be trans. It doesn't matter which is wedged and which is dashed, like between A and B, as long as we have 1 in each. So I'm going to say the top is wedged. And the bottom is dashed. And both of them have a CN. So in this example, are we going to have an endo versus exo product? What do you guys think?
The general consensus.
What's the general consensus? Oh, this would be the perfect time to do a poll. But I'm not there. Sad face.
Wait, can you hear me?
I can now, yes.
Oh, okay. I just gotta lean over to this. Okay. The general answer is no.
Swaggy, and that's what people said in the chat too. So the answer is no. If they are trans, you can't say endo or exo because, you know, there's one going in either direction. And so what would this look like in 3D? Well, you get bam, bam, bam. We have a nice little tabletop up there. And our double bond goes right here. All right, so I'm going to pause for a second. Something that trips students up all the time. He could give you a question like this, and it's super straightforward, but people pick the wrong answer because he'll put a sneaky double bond up here, and people won't even notice it. So just keep track of that, right? Unless we had a double bond here, you're never going to have a double bond up here. Right? So in this class, you're essentially never going to have a double bond up here. So if he has an answer choice that has a double bond up here, cancel that one out, like first thing you do, because it'll look really similar to the right answer and it'll trip you up. But okay, so we're going to have one CN pointing up, one pointing down. Ta-da! I hate the way that looks, but this is fine. Question?
So like the other one only had 1 carbon, but this one has 2 carbon.
Ta-da.
Yeah.
So
Somebody was just asking why the bridge shape changed.
the bridgehead
Like, why it went
changed because that's a really great question. So if we start with a 5-membered ring, we have 1 point in the bridgehead. If we start with a 6-membered ring, we have 2 points in the bridgehead. So that's why it changed a tad. Any other questions?
Somebody has a question. Someone's asking if you drew the CN equatorial or axial.
It doesn't really matter. I drew them equatorial just because that's what I'm like more used to seeing, I guess, because that's what's more stable. But you could have also done it axial, like it's not going to change your answer. Yeah, I won't go too much into that because boats are ugly.
Someone asked if it's gonna affect us on the tests.
The axial equatorial thing, no, it won't. Because to be technically accurate, axial and equatorial is something that you learned on the chair conformation. This is a boat conformation, so it is a little bit different. But as long as you see it, one's pointing up, one's pointing down, you'll be fine. And this could have been the other way, right? Like this one could have been pointing down, this one could have been pointing up. So either of those would have been correct. Yes, what was that?
Someone asked if the largest number of carbons like a diene can have is it 6?
For this class, yeah, it's not going to be any bigger than a 6-membered ring.
Okay.
Cool. So let me just see what other examples I have here. Okay, so we did all the important ones. So I was thinking of spending the last 9 minutes or so doing practice problems. Is everyone okay with that? Or are there any other like questions that you're burning to ask me?
Someone's asking about chapter 14. In regards to...
Did you guys finish chapter 14 in lecture?
We're about to. We're in it. Yeah.
Okay, so chapter 14 usually just takes me one SI session to go through. So I was planning on doing it Friday morning. Yeah. That was my plan. We should be able to get through it as long as he didn't completely finish it today. That should still be a good plan of action. So if you have any like big questions about it, you can definitely ask me over email and I will help you out, or you can watch the chapter 14 video that I have on the YouTube channel. We're going to do it Friday. If I start it now, I will not finish on time. The square one. Okay, so someone asked, will the square one even happen? It will, but it's like a stupid looking one and it doesn't really ever show up on the exam or anything. So I'm going to save it, and then during the exam review, I'll just show you what it looks like because it's in the handout thing. Speaking of the exam review, it's supposed to be this Friday, but we just heard back from Dr. Roche and Dr. West. And I don't know if we're going to be able to finish it on Friday, but I will talk to Katrina like right after this session and I will let you guys know for sure. It's either going to be this Friday or Monday. And then again, if you have any questions about that, you can email me. Everything got kind of messed up this week because I'm stuck in my house and I can't leave. So, but I'll be back Friday. No, so Friday will be in person. So just to clarify, I guess I'll use the last couple minutes just to clarify. So I'm not dying. I don't have COVID. I actually tested negative. I took the test twice and I did like PCR and rapid and everything came back negative. But my dad and my sister had it. They tested positive, but they were sick like 9 days ago and they tested positive like, what was it, a week ago, a week and a half ago ish. So the CDC said I'm locked into my house until tonight, and then I can leave my house tomorrow. I'm going to take another test just to make sure before I come to campus because I don't want to put anyone at risk. But yeah, I should be good to go because all my tests came back negative, and I haven't been around the sick people since I found out they were sick. So should be in person. Everything should be good. The exam review, though, that will have to be online because my boss said so, unfortunately. Today's tutoring hours, I will mention that as well. I may have already talked about that. I probably did. But today's tutoring hours, if you signed up, you will get a link and a confirmation that it's online. And then if you didn't sign up, but you want to... Yeah, what's up?
What's the question? Oh, somebody sent you an email about the link. I don't know what link.
The link.
Oh, if we didn't, someone says it. If someone says that they didn't sign up, can they still get the link? Will they still get it?
Okay, so I'm not gonna send it to the whole class, but if you want the link, email me and I will send it to you. Like if you didn't sign up for the session, yeah, I don't know. I don't think I'm allowed to send it to the whole class. That's the issue. But if you sign up for any of them, or if you ask me to send you the link, I'll just send you all the links for today. I think there'll be 2, and it'll essentially be like the one at 3 p.m. will be a separate link, and then the 5 to 8 session is going to be all one link. So you could just come in and out whenever you would like, if that makes sense. I don't know if I'm explaining it in a way that makes sense, but if you've been to my in-person sessions, you know, like you can leave and come in and I don't make you like leave when your session ends. So that's kind of what I'm trying to simulate online. Also, yes, you were saying something.
Is there a 5 to 8 session on Wednesday? Is that your question? Yeah, someone's asking if you have a 5 to 8 on Wednesday.
Yeah, so Wednesday, which is today, is going to be 5 to 8. And then Friday, I don't have anything. What was that?
Yeah, I think everybody's kind of Gucci.
Okay, swaggy. Well, we have a
Like,
couple
great.
extra minutes, so let's do the practice problems I wanted to do. It's a good refresher. I'm going to stop sharing for a second, though, because I already went through and answered these with people. I don't want you guys to see the answers. Bam. Okay. I'm going to reshare. No, I don't want the video there. Share. Cool.
Anybody else have any other questions?
What? Something question I heard?
No, I was just asking if anybody... I'm just like...
You got the tutor role down. You're like surveying the audience, seeing if anyone has any questions, if everyone's following. I appreciate that. Oh my god. Sorry, someone like knocked on the door so hard and I just like... that scared the shit out of me. Okay, sorry about that. Okay, so this question right here, this one's actually about 1, 2, 1, 4 reactions. And, sorry about that. And it's essentially asking you in the electrophilic addition reaction, aka 1, 2, 1, 4 reaction, and it's at high temperatures, or it's reversible. What do high temperatures and reversible equal? What does that mean? What do we prefer?
I People are saying D.
Yes, so thermo. So that will be D. 1-2 control and 1-4 control are not things. We're just going to talk about kinetic and the thermodynamic control, so you could have knocked those two answer choices out and been down to 50-50. And if it asks you for low temperatures, that would be the kinetic product. Okay, so scroll. Okay. In order for a diene to undergo a reaction, Diels-Alder reaction, it must. So which of the following are required for the diene?
I'm hearing D.
Yes, D. Okay, so what people sometimes struggle with is they're like, well, it could have an electron donating group. What the heck just happened? Go away. It could have an electron donating group. Yes, they do like electron donating groups, but those are not required for the reaction to happen. So we cross those out, and then we don't want S-trans. We want S-cis. Okay, so what about if I ask for most rapid and highest yield for the Dienophile? What do we think?
I think people are going with A.
Yes, perfect. Okay, so the Dienophile is not going to be S-trans or S-cis, so we can knock those out. And then we know we want electron withdrawing groups because withdrawing groups are going to make electrophiles more electrophilic. And donating groups make it more nucleophilic.
Someone has a question. What is it? What is cycloaddition? The question.
Okay, great question. So cycloaddition is just saying that like you're doing an addition reaction and you're making a ring. So that's all that boils down to. So something I mentioned, maybe this was in tutoring. So Diels-Alder reactions are going to be called 2, or actually I'll say 4-2 cycloadditions. Because we have 4 pi electrons here, 2 pi electrons here, and my screen is frozen. There we go. 2 pi electrons here, and we form a ring. So another name is 4-2 cycloadditions.
I think everybody is like mentally pooped.
I feel that. I really do. Yeah, today was a long day. We went over a lot of stuff. So if you have any questions, let me know. I will be here for a second. And then if not, I hope to see your lovely faces on Friday. I missed you so much. I can't wait to give you guys stickers.
Rosemary, why?
Yeah, what's up?
Why would it be more electrophilic help the reaction again?
So, good question. So, the Dienophile is the electrophile. So, anything that makes the Dienophile more electrophilic is going to help the reaction. And then if the question was asking about the diene, we would pick donating groups because we want the diene to be a strong nucleophile. So those groups make it more nucleophilic, so that helps the reaction.
Okay, so if an electron withdrawing group, does that mean withdraw as in form bonds? But I'm not too sure.
Hold on. We're going to cheat for a second. Okay, these are the electron withdrawing and the electron donating groups. So what I mean by donating and withdrawing is they donate or withdraw electrons. So, for example, ignore Bear having a tantrum. If we had NH2, this lone pair right here would donate electrons into the system. Whereas if I had something like this, that's going to take electrons away from the system. So that's all I mean by donating and withdrawing.
Oh, okay. So if it had more withdrawing group, if it had more withdrawing groups, it would get more electrons to use?
It would get fewer electrons. So the electron withdrawing groups are good for the electrophile because they make it more positive. So since these
Okay.
electrons are being taken away, this becomes more positive.
All right.
Okay.
Thank you.
You're very welcome. Okay, guys. Have a wonderful day. And then someone please sign out of the computer just so like...
Yeah, I got it.
Okay, cool. Thank you. Bye. See you Friday. And let me end the recording.